Hi, my name is Kevin, and today I'm going to be giving a short video on Fibonacci heaps, just as they're not really talked about in a lot of current data structure courses or intro data structure courses. I just think they're a really cool thing. So just to start off with Fibonacci heaps, we have to go back a bit and think about what a tree is. So a lot of times in beginning data structure classes, you really only see binary trees. But what is a tree itself? So a tree is just going to be a graph where the number of nodes is one less than the number of edges. And that's all we have to do. So any things with binary trees that you may know about aren't going to be uh, as applicable. So what does this look like? So our most basic tree is just going to have a single node, and then we can slowly keep adding nodes. And for every node we add, we have to increase the number of edges by one. Then you could have something like this, and this is perfectly valid as a tree. But the second that the number of edges equals the number of nodes, or we have one more edge than number of nodes or more, this becomes not a tree. So in terms of Fibonacci heaps, the main type of tree that we'll be using is something called the binomial tree, which is going to be a subset of a tree. So binomial tree, each one is going to have a different order. So the simplest binomial tree, which has order 0, is just going to be a single node. Binomial tree with order 1 is going to have a single node, and then its child is going to be a tree of binomial 0. With order 2, we're going to have a single node, which is going to have one child that is of order 0 and one child of order 1. And this pattern is going to keep repeating. So if we have a binomial tree with order 3, we'll have one child that's 0, one child that's 1, and one child of order 2. And this pattern is going to keep repeating and repeating, and will keep growing. And we'll be using this type of tree specifically a lot when implementing our Fibonacci heaps. Okay, with that out of the way, let's back up a bit to binary heaps, which you have probably seen before from your data structure courses. So a binary heap is one of the most common implementations of a priority queue. So in this video, everything I'm going to be going over is a min heap, but the same thing will be reversible for a max heap. But let's say we have a min heap. So a common binary heap is going to look something like this. And we're going to have two main properties. The first is that this has to be a complete binary tree. So a binary tree is something different from that binomial tree that we were just saying. And this means that every node can either have 0, 1, or 2 children. So in this case, if we look at 8 right here, it has 0 children, 4 has 1, and 2 is 2 children. And we can guarantee that they're all binary. The other thing that we can look at is this complete part. So complete means is that if you ignore the last level completely, so you just kind of look at this part that I've circled right here, then everything has to be completely filled in as much as possible. So, there's no extra space. Everything that's not on the last level of this filled in spot is going to have 2 children, and everything on the last level of this filled in spot is going to have 0 children. And then if you look at this part right here, then everything should be as far to the left as possible. Everything is going to be left aligned, and that is going to be our complete part. So this right here is a complete binary tree. The other thing that needs to be a binary heap is it has to follow the heap factor, where the parent dominates the children. So in the case of a min heap, dominate means be less than, and a max heap, dominate would mean be greater than. So right here, 1 is less than both 2 and 3. 2 is less than 4 and 5. 3 is less than 6 and 7, and 4 is less than 8. And say we know that 4 is less than 8, and 2 is less than 4, and 1 is less than 2. That means 1 is going to be less than everything as we go down that tree. That means we're going to have a guarantee to have our smallest thing always at the root, which will have some kind of point at 2. So if we're going through this binary heap, we're going to have 4 main functions that we'll want to do. It'll be kind of get smallest, which we just talked about. We have a pointer directly to it, so it's going to be an O of 1 operation. Super, super easy. Our next type of operation that we can do on this binary heap is going to be insert. So when we insert this, very review right here, but we would put something in the next spot to make sure it's a complete binary tree. So let's say in this case we put 2.5. Then you would just compare that value with its parent. If it is less than the parent, we would swap and we would keep repeating that as we go up the tree. So this operation is going to be dependent on the height of the tree. So this is going to be a log n operation. A similar function is going to be remove. Where we would do is we would take whatever we have, our root. Remove is going to be removing the smallest thing. So I'll write remove slash delete min. And we're going to swap that with the thing that's at the last level furthest to the right. That's case going to be 8. If 8 wasn't here, that would be 7. The last thing furthest to the right. And we're going to swap them. So that would, in this case, put 8 right here and 1 right here. And then once 1's there, we can remove it completely. And then we just need to percolate 8 down accordingly. So that's also going to be dependent on the height of our tree. So that's going to be another log n operation. The final main thing that we can do on this heap is decrease key. So for any value in this tree, for any value in this tree right here, we may want to decrease the value. There's not going to be really any need to increase the value because this is a min heap. So you want to keep things small. But let's say, I don't know, 6, we're able to decrease it to 0. Well, then this is no longer going to be a valid heap. So we're going to have to percolate that new value up the same way that we just did with our insert. That's also dependent on the height of the tree. So that's going to be log n. So with these main 4 functions, they all seem like they're pretty optimized, especially for this binary heap. They're all around log n, which is pretty good, and the exception of get smallest, which is O of 1, sorry. So how does this change for a Fibonacci heap? Well, a Fibonacci heap is actually going to have a lot of different runtimes, so we're going to kind of go through these one by one as we define what a Fibonacci heap is, and use them to build our idea of the Fibonacci heap. And then as I'm saying this, I'm going to kind of jump around and keep adding more and more properties, and I'll fully draw them out as I add them. But the things I draw at the beginning, things I draw at the beginning might not be super accurate to what a Fibonacci heap is, but as I keep adding properties, they'll start to build together. Okay. So in terms of our actual Fibonacci heap, we're just going to basically have some lists of these binomial trees that I was just mentioning. So we're going to have something right here called our root list, which is going to be a doubly linked list. And it's going to hold a bunch of different roots. So maybe we have a tree of order 0, order 1, a 0 here, a 2 here, a 0 or another 1, and let's add a 3 as well. And just like that, you're basically looking at what a Fibonacci heap can be. And everything is going to be doubly linked right here. In addition to this, we're also going to have every child of a certain node be doubly linked. So right here, these two are children of the same node. So there's going to be a double link right here. Same thing's going to be happening right here and right here. We have all these extra connections that we have to account for. And most things that we do going forward, I'm not going to fully draw this out because it's going to get really messy. But it's important to note that all of these things are here. And finally, the other thing that we have to have is we have to have a pointer to whatever our smallest node is. So if we just go back for a second and look at these heap properties, the first was to have a complete binary tree, and the second was that the parent dominates the children. So we've definitely gotten rid of the idea of a complete binary tree. We have a bunch of trees, none of them are complete, and none of them are binary. There's also no connection between, like, say, this one and this one. Like, it's not like the smallest has to be all the way on the left. There's nothing of that kind. The only thing that does really matter is that heap property, where the parent dominates the children, and that's going to be present. So if we look at this binomial tree of order 3, this node is going to dominate all 3 of these children. And this node is going to dominate all 2 of these children, and so on. And then nodes where it's just of order 0, well, they're just kind of there. Okay, so now let's go in that first function that we did before of get smallest. Well, I mean, just looking at this, I just said we have a pointer pointing to the node or the tree that has the smallest node. and the smallest node would have to be at that root of that tree. So it's going to be guaranteed that this is always going to be our smallest. So super simple. We're already done. Get smallest is trivial. It's just going to be O of 1. So far, we're doing good. We can't really optimize get smallest any further. It's going to be a constant operation. But now how do we handle insert? And this is where it's going to start to get a bit weird. So let's imagine for insert that we want to be as lazy as possible. So I'm just going to draw out a quick tree with a couple numbers in it. Just random numbers that I'm thinking of off the top of my head. And this is going to be our root list right here. And let's do a couple other things. 11. And yeah, honestly, that's good enough. So right now, as this tree is, we're going to have the pointer to our smallest thing right here, which is going to be 9. And then our first step of insert is just going to be to add a whole new tree. And the reason we want to do this is we want to try and make our insert as fast as possible. And to do that, we're going to be as lazy as humanly possible. So in all these pictures I've been drawing, we have trees that are just order 0, just kind of floating around. So we're literally just going to do that. We're just going to add a complete other tree of order 0. So let's say I want to add 2. Boop, we just stick 2 right there. And then the second step of insert is going to be check for new min. So in this case, 2 is indeed less than 9. So we just need to update this pointer, which is just one comparison. That's a constant operation. And just like that, we have our insert. It's that simple. So insert is actually going to be O of 1 for a heap. Okay, so sorry, for Fibonacci heap. So it seems like we're starting to have some different big O. But you might be thinking, well, if this top level is just a doubly linked list, and we're just adding things one at a time to this list, how is this actually a heap? How is this doing anything for us? So what we'll be doing is we need a way of cleaning up. So what's going to happen is every time we do this remove or delete min, we're going to also do a cleanup. So what does this do for our big O? So let's say that if I insert something, it's super simple. So let's say the cost of doing an insert, which we just said was O of 1. Let's say that takes, I don't know, 2 seconds. Pretty simple. And let's say I do that 100 times. And every time, it's just going to be taking 2 seconds. Doesn't matter how big our list is, it's still going to be just the exact same work. Okay, so now I do a single delete min operation. And that's going to take me, I don't know, 255 seconds. Okay, that's a lot of work. But then during that 255 seconds, we're going to be doing a bunch of cleanup. Then if I do another delete min right after that, it might only take me 40 seconds, which is a lot better. So this taking a super long time is dependent on having a bunch of inserts right before it that are really, really quick. So we're going to do something called amortized analysis, and we're basically going to say that that work is kind of pre-processed. Because if we did 100 insertions, we can kind of think of this 255 right here as 2 times 100 plus 55. And we can take all that extra work from those 100 twos and kind of put one into each of the previous O of 1 operations that we did. And that's just kind of doubling the length of this O of 1 operation. And we know in big O terms that O of 1 times 2 equals to O of 1. We can basically say we're just going to get rid of all this work right here and distribute it into our previous 100 operations. Because again, delete min is only going to be slow if we just did a bunch of inserts right before it. So it's kind of like saying, even though the work hasn't happened yet, we're holding space for this extra work to occur. If that didn't make a lot of sense, there's a lot of great videos on that on YouTube. That's going to be called amortized analysis. Another example of this applying is if you're like write in a stack and you have to do resize, it's going to be the same methodology there if you've heard of that before. Okay, so with that taken into account, that we can kind of distribute this extra work from delete min into our previous inserts, and kind of the cleanup is covered in there. How do we actually do this delete min function? So I'm going to write out kind of the methodology as we do it, and for each step, we're going to give the big O. We're going to be able to prove the big O of this as we learn the methodology. And I'm just going to be working with this tree right here as we do that. I'm just going to copy this down. All right, perfect. So the first step that we're going to want to do, or so if we're deleting min, we'll be deleting this 2 right here. And let me just add a couple other things so we can have a bit more of a tree to work with. Okay. So the first step, and actually, I'm just going to add some children right here, make it a bit easier to also visualize some things that are going on. So now this tree is of order 2. Sorry. So for the first step, we find node to delete, and we're going to break up the children. So again, if we were doing things like a normal binary heap, we would have to percolate things around. And that's going to be dependent on the height of the tree. And we want to avoid that as much as possible. We don't want to have to be jumping around between our own trees because that can make our things quite slow. So we already know that we can just kind of add things to our list. That's exactly what we're going to do here. This node that we're trying to delete has 2 children. So we're just going to break them up completely. So 3 is just going to go over here and it's on its own now. And this tree right here that starts with a 4 is just going to come over here and it's on its own now. And now we can just delete 2. And that's going to be step 2. So, that list was doubly linked. So deleting that one that we already had a pointer to, that's just going to be O of 1. And breaking up the children, that's going to be a bit more complicated. So if we have a node with 5,000 degrees, it's going to have 5,000 children. If we have a node with 5 degrees and 5 children, then it's going to be like, we have to move 5 things over. So this is going to be dependent on the max degree of a tree, the big O of this. Big O is our worst case. So if we have a node with a really big a heap with a bunch of trees, we want to assume that we're breaking up the one with the biggest max degree. That's our first step. Okay, we're doing good so far. So step 3 is going to be to clean up. And this is the most little complicated part of this specific algorithm. So in order to do that, what we're going to do is we're going to make an array. And when we make this array, we're going to assume that we know what the maximum degree size of this tree is going to end up being. I don't know the exact one for that tree I drew up there, but I'm just going to assume that it's going to be 4 and hope for the best. Then what we're going to do is we're going to kind of iterate through our list right here, and we're going to kind of just put each thing where its degree is. So this first thing right here has degree 2, so I'm just going to stick it in the spot that says degree 2. Our next tree has degree 0, 11. We're going to put the one with 9 and 10 right here. Then we hit 14. When we put 14, there's a collision. So every time there's a collision, we're just going to merge them. So 11 and 14 get merged. 11 goes on top of 14 because it's smaller. And now this tree has degree 1. We're going to move it up. And that's going to show up in the degree 1 spot. Another collision. 9 is smaller than 11. So 11 goes on the right of 9. And just like that, we now have a degree 1 tree right here. So this is going to get moved up as well. Collision. 9 is smaller than 13. So 13 is going to get connected right here. Let me just organize this a bit easier to see. And 13 is going to become the rightmost child. And now we have a tree of degree 3. And this gets moved up to this spot. We come back up here, we just did 14. So our next value is going to be 21, which is going to go right here. Then we'll add 16, also go right here, collision, move up a level. Then we'll add 3 right here. And then we're going to have to add 4 and 5. That's going to connect. That's going to move up to be degree 2. And just like that, we did all our cleanup. So our tree after cleanup is going to look like 3 right here, 4, 5, 16, 21, and this big tree of degree 3. And here is a nice cleaned up tree. Okay, so with that algorithm, what is the cost of doing this? This is going to be O of the number of trees, because we had to iterate through this list with, all of our trees, this list right here. Plus, we also had to iterate through this part, which is the number of trees that are going to be in this part is the max degree. If, whatever tree was right here, if this had degree 5,000, and there'll be 5,000 extra trees right here. Just the O of the number of trees plus the max degree. And then in terms of the merges, well, theoretically, we could have to merge on every tree. So it can be up to the number of tree of merges. Okay, now for our next step, which is kind of what I already did. So after we build this array right here, then we need step 3 right here, or step 4, sorry, which is to build a new root list. And that requires iterating over this list right here. That's going to be O of the max degree. Let me just reorder this a little bit. There we go. And this part right here is O of the max degree. And finally, step 5 is to find the smallest, which is going to be O of number of trees. So we'll have to iterate through this part right here and find the smallest, which is going to happen to be 3. And we just need to set our smallest pointer to 3. So with all that work combined, there actually pretty much is a bunch of variations of max degree and number of trees. So we have O of max degree, max degree, max degree. So it's 3 max degrees total, right? Yeah, that's O of max degree times 3 plus number of trees right here, number of trees right here, and number of trees right here. Number of trees times 3. Okay, so in terms of the number of trees part, that's the part that we said would be amortized into our inserts. So all that work from the number of trees and changing that number of trees gets factored in to our insert. So this is just fully amortized, and we can actually ignore this in our big O. We can also ignore this times 3 right here, because constants don't matter in big O. So our big O is actually just going to be O of the max degree. So if we can bound what our max degree of our tree is, then we're actually going to be able to determine the big O of this specific operation. So if we think back to what we were doing right here, every single node that we inserted into this array was already a binomial tree. Oh, sorry. Because everything right here was a binomial tree. And by merging binomial trees together, all you do is make a bigger binomial tree and a bigger binomial tree. So we know that everything that we have is going to be a binomial tree. The other thing we know is that we're not going to have multiple binomial trees of size 0. We won't have multiple binomial trees of size 1. If there's a collision, then we merge them up and make a bigger binomial tree. So because of that, depending on the max degree, of our tree, we know the number of nodes that we have. So if we kind of draw this out, so let's say a tree is degree 0 at max. If the tree is degree 0, we can only have a single node. If the tree is degree 1, well, let's see how many nodes we can have. We can have a degree 0 tree and a degree 1 tree. And that's it. That's going to give us 3 nodes. Let's keep going. Let's say our max degree is 2. Well, then how many trees will we have? We'll have a degree 0 tree, a degree 1 tree, and a degree 2 tree. And that's going to be 7 nodes. And hopefully you're starting to see a pattern where it's times 2 plus 1, times 2 plus 1. The reason for that is, well, we're taking the previous tree that we already had, and then we're adding a new node, and we're basically having the children of that new node also be the previous tree that we already had. So based on that, if we add a tree of degree 3, it should have 15 nodes times 2 plus 1, and we're going to need a degree 0 tree, a degree 1 tree, a degree 2 tree. So that's our 7 from the previous tree. Then we'll add an extra node for our degree 3 tree, and its children are going to be everything that we've already drawn out. This is the same as this right here. Just like that, we know that the number of nodes that we have, depending on our max degree, grows exponentially. So because of that, as this grows exponentially, that means that our max degree, or sorry, the big O on the max degree is going to kind of grow logarithmically. The number of nodes we have grows exponentially compared to the max degree. So it's basically saying that our max degree is log n of the number of nodes we have. Okay, so if we head all the way back here, our remove slash delete min is now proved to be log n, and we're able to achieve that with an O of 1 insert. Now the thing that we need to keep in mind is this decrease key. That's just our last thing that we have to do. And this is where it's going to get a lot more complicated. Let's take this nice tree that we built up in the previous step. All right, let me just write this out. Decrease key. So there's a lot of things that can happen. So the first case is our super, super nice case. And that's we don't have to do any work. So right here we have a 16, and let's say I decrease this to a 12. Well, 12 is still less than 4. We violated no properties. Everything's fine. We don't really care. So that's the first step. Check if it's fine. If it's actually fine, we're just not going to do any more work and we're just going to move on with our lives. But what if it's not fine? So what if the value is less than the parent? Before I say that, the value will never end up being less or greater than the parent because we're only doing decrease, not increase. But let's say we were to decrease 16 right here and we wanted it to become 3. Okay, 3 is definitely less than 4, so we need to change some things. So the easiest thing to change is if we're kind of using that mindset that we've been using this entire time of being lazy, is let's just make this not a child of 4 anymore. And I just move it over here. Okay, that worked. Now 4 is degree 1, and 3 is also order 1. And then, doing all these extra operations that move trees over, we can just rebuild our tree later. Next time we do an extract min, that work will be amortized just like it was for insert. Okay, so it seems pretty okay, right? Not quite. Because what happens if we look at this tree that we had right here? So if I just copy this down and bring it down a bit, well, some things are going to get weird. Let's say I reduce this key, and then this key, and then this key, and then this key, right? That's 3 keys. So I just say I reduce them all. And now we have like 8, 7, 6, 5 over here for reducing those. Using that same mindset we were just doing. As we get bigger and bigger trees and we keep doing reductions, we lose the ability for these to be true binomial trees. And you can see that right here. This isn't really following those properties of binomial trees anymore. This is just a tree that just is kind of existing. And we can kind of do this on larger scales and really break up our binomial trees. And we just said up here that this whole thing of our max degree growing logarithmically to the number of nodes depends on these being binomial trees. This whole thing we drew out said this has to be a binomial tree. And we just said they're not binomial trees anymore. So we have to come up with some compromise. So how do we do that? Well, a compromise is going to be per node, we can only cut one child. Okay, so let's see like what this is going to actually end up looking like in practice. So if I just draw out a big node right here, so it's been, messed with a little bit, something like this. Then we're already going to have something have been cut right here, and so it will already have been cut right here. So when something is cut a single time, we're going to mark it and say, 8 has had one of its child cut, 5 has had one of its child cut, which, makes sense because this should, yeah, yeah. Um, so now let's say I want to decrease the key of 9 right here, and I decrease this to 0. Well, 0 is going to be less than the parent of 8, so it makes sense that we would want to, after we do that, kind of start to break this up. So 0 would come down here with 10 as its child. But now if we were to do that, that kind of messed up tree would look even more messed up because this would be fully gone down here. But we just said that 8 has already been marked, which means we're basically going to now remove 8 as a child completely. And 8 just going to also come over here. And now 8's gone. But 5's also been marked, and 5 just lost its child as well. So now 5's also going to move over here with its children. And now 1 has lost a child, so 1 is going to have a little mark. And that's how we can kind of do a compromise. We can only remove so many things at a time. Okay, so at this point, let's discuss what the big goal of this operation is, and then why this still works in terms of our growth over here. So in terms of the big O, all we do is we pretty much check something and then drag it out. So we check, then drag out. That on its own seems fairly simple. That kind of seems like we're on the verge of an O of 1 operation. But you might be thinking, well, right here we had to drag out 1, 2, 3 things. And theoretically, that can go over and over. This is, a recursive thing as we're going upwards, where we have to remove more and more things. So is there a case where we have to remove possibly every single node? And there is a case, but it's a bit more complicated than that. So at any point, I can only mark one thing with a star when I do a singular decrease key. So I can only remove one child at a time. It's not like I'm removing 4 children from the same node with just one decrease key operation. So you can kind of think of it as with one decrease key, we're doing 2 things. We're marking one node, which is, not that much effort, and we're bringing one child out. Again, not that much effort. Everything here is O of 1 so far. For the case to happen where I, move 3 things out, well, there already had to have been 2 things that were marked that didn't get moved out. We can kind of rephrase this as instead of marking one node, we're just going to account for doing the work of moving that node. Now we can think of a decrease key as bringing one child node out and potentially moving one other node, which is just two things that are both constant. So that's just O of 1. Moving a bunch of nodes out depends on having done a bunch of decrease keys previously, which means we can once again amortize that work together to say it's just a single thing that we have to do. So just like that, we've written decrease key to be O of 1. That's great. But if we're still doing this other work where we have this weird looking thing that's not really that same binomial that we started before, how do we know that this still allows node degrees to grow logarithmically? And that's going to be the main hook that makes a Fibonacci heap. So let's think a bit back. So if we have, a node right here, let's say we have a bunch of children on it. We're just going to label as y1, y3, y1, y2, y3, and y4. So for these to have been merged together, when y4 was added, then this node right here is going to have at least 3 children, and y4 has to also have at least 3 children for them to be merged together. So this one right here, 3 kids. Y4 also has 3 kids. And then at any point, we can remove one child from y4, and that's kind of it. So y4 can go down to 2 kids. Okay, so 4 to 2. If we add y5 over here, well, for y5 to be added, this parent node right here has to have at least 4 kids on it. So y5 should also have 4 kids initially. And then if we do that thing where we remove only one child from y5, well, that's just going to go down to 3 kids. So that means if you're the kth child, then your degree is going to be k minus 2 or bigger. So keeping that property in mind, what did these trees start to look like? Well, if we go back to our smallest tree possible, then we're going to have, once again, just a node. Actually, let's number these. Well, just one. And this one right here, we can't really break apart just like we did, like, our order 1 tree. Because if we broke 2 apart, then it would just become 2 trees of degree 0. Our smallest tree of degree 2 is going to start to look something like this. 'Cause, if we remove this, it would be gone. If we remove this, it would be gone. And so all we can do is delete this child that was right here. That's our only option. Let's look at what the next tree is going to be. Next tree is going to look something like this. So once again, all we can do, we can't really do anything here. We can just delete this one child right here. And then for 4, we deleted this child right here. That's the most number of things that we can delete from this degree 2 subchild right here. And let's do one more of these. So this part right here all looks the same. And then that broken up degree 3 subtree is going to look something like this, where we deleted the biggest child we could, the one with order 2 right here. So what we deleted was this many nodes. And if we're looking at the number of nodes in each of these trees, it's kind of going in a familiar pattern. 1, 2, 3, 5, 8. Okay, starting to look interesting. The other thing that we can note is that the beginning of this tree was the one right before it, and its new child that we're adding is the same shape as 2 before. So let's do one more tree. Well, that new tree is going to start, the smallest tree that we can have degree 5. Oh, sorry, did not copy this. Is going to start with our smallest tree of degree 4. So exactly one thing before. And then the tree of degree 5, when fully broken up, is going to only have 3 degrees, which look like this. That's the smallest tree you can have of degree 3, which is going to be one thing in the chain before. So we're adding the number of nodes that we had in the chain right before this, in the chain 2 before this, which is the exact Fibonacci sequence. And because we know this is growing at the exact Fibonacci sequence, that means we're able to determine the rate at which the number of nodes is increasing. One of the facts of the Fibonacci sequence is that it increases at a rate of around this, which is around 1.618. So our number, as we increase our max degree, the number of nodes we have will be increasing at this rate. And because of how big O works, this is still just going to converge to a growth rate of log n. So with all that in mind, where do Fibonacci heaps actually come into play? There's not a super direct applications because there is a lot of overhead as we've seen. Our big O can improve in certain cases, but it's only if we're doing a bunch of inserts and a bunch of decreased keys. The most common applicate or algorithm where this is actually used is going to be Dijkstra's, where we have to do a ton of inserts and we have to keep decreasing the keys. But it's only going to be directly applicable with an actual decrease in runtime if we have a ton of nodes. Same thing with something like prims or kruskal's, which are some other graph algorithms. They're all going to, have some increases with the Fibonacci heap. So it's not going to be the most applicable thing, which is why it's not taught in a lot of courses anymore. But it's still just a really cool data structure. I hope you enjoyed that, and thank you for watching.